Once we are comfortable with the idea that the derivative of a vector-valued function gives us a tangent vector to the parameterized curve, that really only kind of tells me information about the direction that this vector, the derivative vector, points. Right? It doesn't by itself, that observation by itself, doesn't really give me any information about the length of this derivative vector, because it looks like that length does change quite a bit along this parameterization. Like back here, it looks like we have a very long tangent vector, whereas in sort of some of these other places, it looks like the tangent vector is considerably shorter. So that idea of tangent specifies direction, but we need to get a notion of length, magnitude, norm. We need to get that notion from somewhere else. And so what we do is we define, we just make a definition that the length of the derivative vector is what we are going to call the speed of the parameterization. So when we say the word speed, we're always talking about a scalar quantity rather than a vector quantity. And so the speed is what we call the length of the derivative vector. So just to kind of make a little table of terminology here as we go on, I'm going to switch over to my whiteboard, that if I have a parameterized curve, parameterized by the vector valued function r of t, then its derivative vector is r prime of t, which we can compute by taking derivatives one component at a time. And its direction, the direction of this derivative vector, gives us a tangent to the parameterized curve. And its norm, its magnitude, is a scalar quantity that we call the speed of the curve, or the speed of the parameterization. And because in physics we have this terminology also of whenever we have a rate of change and a speed, and that rate of change is equipped with a direction in it also, that a speed that also has a direction associated with it is typically called a velocity. And so for that reason, we also often call the derivative vector a velocity vector for this parameterized curve. So I'll just sort of put that terminology here. So anytime we see v of t, we sort of think of it as the derivative r prime velocity vector. So that is sort of a lot of information that we can get out of just the first derivative of a vector-valued function. Right? The magnitude tells me the speed, and the direction tells me the tangent. Taken together, they tell me the velocity vector of the parameterized curve. So coming back into our activities, we'd like to understand a little bit more about both velocity and also, you know, what's good for the first derivative is also good for the second derivative. We could sort of attach similar terminology to that second derivative. So the derivative of the derivative, r double prime of t. Again, taking our cue from physics, the derivative of a velocity in physics is typically called an acceleration. And so that will be where we get an acceleration vector from, and we'll call it a of t in this case. And the cool thing about the acceleration, right, is that it tells us how the velocity is changing. And so the magnitude, well, I guess this gets a little bit, the terminology gets a little bit strange, but the magnitude of the acceleration vector is something that we might just call the scalar acceleration of the curve. It's how it's actually kind of an interesting question. It's not exactly the same thing as the rate of change of the speed. So I'm just going to kind of flag that in here because that is one of the exercises that's a part of these set of activities. Not necessarily the same as the rate of change of the speed. And these activities, I think, are going to give us an intuition as to why that might be the case. For the most part, we're going to want to treat acceleration and velocity in their full flower as vectors, and be very cautious when we speak of their magnitudes or their directions in isolation, because the relationship is not necessarily as clean cut as we might sometimes want it to be. So in our activities, I think the right way to sort of finish things up today is to work through activity number 4. And in this activity, it starts out by giving us yet another parameterized curve, for which I will send a Desmos link to help out with this again. You're asked, first of all, to just compute the velocity and acceleration vectors. Those are going to depend on t, right, because they're different at different places. And then parts D through G here, and I'm going to have you do part D and part E and part F. But I've done part G in the notes, and I've done part C in the notes. But those parts are the ones that are going to give us a glimpse into how velocity and acceleration vectors kind of carry information about the way that a curve is moving and how speed is changing. So that's kind of the goal here for this last activity of the day today. So now that we've figured out the velocity and acceleration vectors, and notice that the acceleration vector is actually constant in this example. It's always -1, 0, so it's just pointing toward the left with a magnitude of 1 everywhere. The question now is, how can we use this information to tell us something about how the speed of this parameterization is evolving in time? So the speed is the magnitude of the velocity vector. And because it's a magnitude, we can compute the speed using a dot product of the velocity with itself, right? Because the magnitude of any vector is just the square root of its self dot product, right? Its dot product with itself. And so what that allows you to do then is to determine, first of all, a formula in t for the speed of this parameterization, and it can show you, once you look at that formula, when the speed is large and when the speed is small, for example, right? So that's going to be your first task. And then, and this is the interesting part, what I'd like for you to look at is sort of at what points is this parameterization speeding up, and at what points is this parameterization slowing down? So when is it accelerating? When is it decelerating? And what does that have to do with the angle in between the velocity and acceleration vectors? So because we've got dot product back in the mix, we can talk about angles again. So that's parts D, E, and F that I'll let you start looking at. So step 1 is that computation of the speed function as a function of t. And then in parts E and F, connecting it to the orientations of the velocity and acceleration vectors. So in this activity, what we're trying to do is get a sense for how the speed of a parameterization changes, and how we can know when a parameterization is speeding up, when it's slowing down, and when it might be moving at a constant speed. And so what you figured out in this example, just by computing the speed function as a function of t, its graph looks something like this. We expected here that the speed of my parameterization was decreasing up until t equals 2, and then after t equals 2, the speed started increasing again. So we're slowing down until we hit t equals 2, and then we're speeding up again. And on our graph itself, that was sort of borne out by the picture, right? That my velocity vectors look really long here, but they're getting shorter. And then when we hit t equals 2, that's the shortest possible of the velocity vectors that we get, because once we turn that corner, they start getting longer again. And the really interesting observation that you're sort of making here is that it probably has something to do with the angle between the velocity and the acceleration. After all, the acceleration vector is telling us how the velocity vector is changing. Both how its magnitude and its direction is changing. And so the conclusion that you came to was that when the velocity and acceleration make an obtuse angle is when we seem to be slowing down. And one way to look at this, right, is that if I'm traveling in this car along this curve, right, I'm going forward, but the acceleration is kind of pulling me backward, and so it's slowing me down. Whereas when those make an acute angle with one another, then the acceleration has some component that faces parallel to me instead of anti-parallel, and so it's contributing to an increase in my speed as I go along. And so the one place where my speed is neither increasing nor decreasing is this point right here. And what relationship do the velocity and acceleration vectors have to one another at that point?
They're equal.
Well, actually, in this example, they are equal, but
They're perpendicular.
And they're perpendicular. So they won't always be equal, but they will always be perpendicular at a place where the where the speed has stopped increasing or decreasing, right? It's neither increasing nor decreasing. So what the last part of this problem invites us to do is to prove that.
What Paddy?
So the big finish, the big conclusion that we're meant to come to here is that we can use the angle in between velocity and acceleration to tell us how the speed changes. And the reason that we can do that is that the speed is nothing more than the dot product of the velocity vector with itself and then modulo a square root, right? And so in part F, what we want to do is take the derivative of the dot product of velocity with itself. And there's a tool we can use for that in the properties of derivatives of vector valued functions. So derivatives, just like in single variable calculus, distribute over addition and subtraction. They distribute over scalar multiplication. In this case, a scalar function even can be out in front. But the cool thing is that they also have product rules. There is a product rule for derivatives of vector valued functions, both with respect to a dot product. So the derivative of a dot product is the derivative of the first one dot the second one, plus the first dot the derivative of the second. And there is also a derivative rule for the cross product. That is a product rule as well. The derivative of r cross s is r prime cross s plus r cross s prime. And there's also a chain rule, which is this number 5. But it's this number 3, the dot product rule for derivatives, if you like, that we could use to investigate this part F. So it says use that product rule to express the time derivative of the dot product of v with itself in terms of both the velocity and the acceleration. So I'm just going to sort of type this one piece up here. So what we're trying to do is find the derivative of the dot product of the velocity with itself. So this is the derivative that we're trying to compute. And so according to the dot product rule, this should be equal to the derivative, I'll just call it v prime, dotted with v. So it's the derivative of the first dotted with the second, plus the first dotted with the derivative of the second. Right? So this is using the dot product rule. Okay, but then what do we know about v prime? What's another name for v prime? The derivative of velocity is otherwise known as acceleration. So this is the dot product a dot v added to the dot product of v with a. Yes, I'm writing LaTeX code in front of an audience. Sorry. There. So it's a dot v added to v dot a, since derivative. Okay, but what else do we know about the dot product? What is the relationship between a dot v and v dot a for a dot product?
The same.
They're the same. So cross products had an anti-symmetry to them. So you get a minus sign when you switch places. But dot product is symmetric, so that a dot v and v dot a are the same thing. So this is really nothing more than 2 times either a dot v or v dot a, whichever one you prefer. I'll do v dot a using the symmetry of dot product. So what we have all in total here is that when I take the derivative of the dot product of the velocity with itself, what I get is twice the dot product of the velocity with the acceleration. So what this tells me is when velocity and acceleration make an, let's say, well, let's start with the right angle. What should we be able to conclude when velocity and acceleration make a right angle? What is their dot product?
0.
It's 0.
Mm-hmm.
And so the time derivative of v dot v is also 0. In other words, that's the point at which the speed is neither increasing nor decreasing. And so that was the point in our example that we were just working on. That was the point right here. Right, that was the point where my velocity was neither increasing nor decreasing because the velocity and my speed was neither increasing nor decreasing because velocity and acceleration were perpendicular. That was this point when t was equal to 2. Okay, and then just to verify that the rest of our intuition from this exercise also worked, what can we know when velocity and acceleration make an acute angle? What can we say about the dot product of two vectors when their angle is acute?
Is it positive?
Yeah. When we learned about dot products, and that was actually only just yesterday, this was one of the big takeaways from the dot product, is that acute angles between vectors result in positive dot products. And so a positive dot product of v with itself is going to result in a positive time derivative for the speed. So the speed would be increasing at places where the angle is acute between velocity and acceleration. And of course, that would mean that when the angle is obtuse instead of acute, that we will see the last thing, right? That we'll get obtuse angle. And when velocity and acceleration make an obtuse angle, the dot product is negative. And so the time derivative of the dot product of v with itself is also negative, and so my speed will be decreasing. Cool. This is a subject that's very near and dear to my own heart because in graduate school I did my doctoral dissertation on celestial mechanics. So it's the physics and mechanics of planetary motion, most of which is built around what are called central force problems. If we just consider the sun and the earth and how the earth is orbiting around the sun, that's called a central force because the reason that the earth is held in its orbit is that it's feeling the gravitational pull from the sun, and that pull is always perpendicular to the direction in which the Earth is actually orbiting. So the acceleration that the sun imparts on the Earth by way of the gravitational force and the velocity of the Earth's orbit around our orbital path are perpendicular to one another, roughly speaking. There's a little bit of a correction factor there. But if in the case where they're perpendicular to one another at all times, that's the reason why, if you're moving along a circular orbit in a central force problem, that you're moving with a constant speed. And so up to that first approximation, the Earth's orbit around the sun is at a constant speed because that force is always perpendicular to the direction of our motion. For the same reason that the diameter of a circle, or the radius of a circle, is perpendicular to any tangent to that circle. So yeah, this is the sort of the beginning of that, of a lot of study of mechanics in physics, is this kind of relationship between acceleration and velocity.